Hey there, grade 12s. We will be reviewing the calculations associated with a weak acid and strong base titration. These also follow the pattern for a weak base and strong acid, just in the opposite direction. Anywhere we calculate pH would be POH, which can then be converted. So we're going to start off with the theory of this, and then we'll get into the calculations, because these stages kind of explain what happens. A weak acid or a base will always be titrated. I'm going to set this up by a strong acid or base, because we choose the titrant, so we wouldn't choose a weak solution because it would introduce an equilibrium and potential error. So the titrant will always be strong. The sample can be strong or weak. In this case, it will be weak. So what happens? There's two main steps to remember. Number one, there's a reaction. Acid plus base produces water and salt. The salt and whatever's left over then enter an equilibrium, right? So assuming this is an acid, the acid plus water will generate H3O plus and some negative anion. Okay, we'll call this HA in this case, because it'll give the water a proton, leaving behind the negative portion of it. This equilibrium here is what affects pH, because it has the hydrogen concentration in it. And for a base, it would have hydroxide instead. So we'll set up all of our problems like this. There's a couple of shortcuts we can use theory to simplify, and we'll do that first. Okay, but these are for any titration involving a weak species. There's the stoichiometric value, right? And then the excess, which is determined by subtracting the amounts that react in a 1-to-1 ratio, will begin an equilibrium that determines the pH. So, stage one. If we were to break our titrations down into 5 stages, this is how we would do it. Before the titration begins, there's only the weak analyte. So there's an equilibrium, and we'll use an ice table. And the K value, A or B, depending on if it's an acid or a base, to determine hydrogen or hydroxide, and then calculate pH based on that. So that'll be the same for the beginning of any titration. After that, at any point before the equivalence point, what we have is a buffer, because during the reaction, some of the sample, or the analyte, is converted to the salt as part of the reaction you can see above in part 1. That salt is the conjugate of the sample. So because there's a sample, there's a substance and its conjugate presence, that's what a buffer is. And there's an equation to work with buffers to simplify it. So that equation is called the Henderson-Hasselbalch equation, and it is pH is equal to pKa plus the logarithm of the conjugate over the acid. For bases, it would be the opposite. It would be Kb plus the log of the conjugate over the base. And those are the concentrations of those substances. So those are important points. Anywhere between the beginning and the equivalence point of a titration, this equation, called the Henderson-Hasselbalch equation, combines an ice table. I'll just jot that here. Combines an ice table, the K calculation, and the pH calculation into one step by simplifying it. So all we need to know is the concentration of each species, and then we can apply that equation, which is what we'll do. At the halfway point to the equivalence point, what happens is that the acid and its conjugate are in equal concentrations, and they cancel each other out. So by canceling out, the concentration of hydrogen is equal to the K value, or Kb will determine the hydroxide concentration. And we can say that the pH is equal to pKa, or negative log of the Ka value. The P represents the negative log in our terms. So these are all ways, just to remind you, of calculating the pH throughout a titration, and we'll go through the example calculations for that. Now, at the equivalence point, the product of the reaction is an acidic or a basic salt, and what that means is that the pH does not equal 7. It'll be above or below when there's a weak species present. So what happens? If the sample, is a weak acid, when it reacts with the base, it will produce a conjugate base. Okay, so in this case, some hydroxide carrying base reacts with the weak acid to produce water and an anion. That's the reaction. That anion, because it's the only thing present, will interact with water to generate an equilibrium. Right? And as part of that equilibrium, because it's a weak base, it will accept a hydrogen from water, leaving behind hydroxide and the original acid. Now the hydroxide is what determines the pH, so we'll use that. We'll determine its concentration to figure out the pOH and then the pH. Now because the conjugate is acting as a base, we need to determine its Kb value for that reaction. Okay, so we do that by dividing the K value for water by the K value for the acid, as we discussed in previous lessons. Setting up an ice table, that would be products over reactants, and from this equilibrium here, the products are hydroxide, HA, and the reactant is the anion. So all of this is the same but opposite for a weak base. You can see that there's a reaction and an equilibrium there as well. So to determine the pH at the equivalence point, we need to write an equilibrium for the salt and use a K value for that to determine the concentrations. After the equivalence point, only the titrant is in excess. Now it's strong, so it determines the pH stoichiometrically. There's no ice table involved. So we'll just put that here. Right, and any salt that forms is not going to contribute to the pH because it will be too weak to dissociate. So that's an overview. I'll get into the calculations now. I will go a little more quickly through the calculations, but be sure to refer back to this section if there's something that you didn't understand or would like to review. So in this example, what we're going to do is to sketch a titration curve. Now, to do that, we need 5 pH points to make this accurate, right? And they'll be the 5 points that we talked about above. So we're reacting acetic acid, which has a formula of HC2H3O2. We're going to shorten that to HAC here. And AC is just short for acetate, which is what that anion is. And that's reacting with sodium hydroxide. So the sample is the acetic acid because it's the weak species. The strong one will always be the titrant, and we were given the Ka for this. So before we begin, there's 2 reactions, right? There's number 1, the balanced reaction, the neutralization, and then there's the equilibrium for the salt. So we've got acetic acid, and we're going to simplify that here. Okay, that replaces all the letters, plus sodium hydroxide. Notice how it's one way because it's a water. It produces water. It's one way because it's a reaction. Plus sodium acetate. All right. Now, the sodium ion does not affect pH. It's a metal, so it doesn't interact with water as an ion. But the negative part, the anion of the salt, will in this case. So it's negative, and when it comes into contact with water, an equilibrium is established. I'll just fix that up. So now that's the conjugate base, okay, because we started with a weak acid. So when it loses its hydrogen, it's willing to accept it back, and it acts as a base. So when it interacts with water, it will do that, and it'll generate the original acid plus OH minus. So that OH minus being present is what will determine the pH at the equivalence point that we'll see later on. So we need these to see that everything is a 1-to-1 ratio. And now we can proceed. So I'll wrap that up there. I'll call that part A. And in part B, which will be a continuation of this, we'll go through the calculations so we can have the video split into a couple of different parts.